So over the past couple of classes, I've talked about hypothesis testing. And I did start out saying there are 3 different methods to test hypotheses. Usually but however, all the examples I did, I just relied on something we'd practiced before, calculating confidence interval. If you know how to calculate a confidence interval, you know exactly how to test a hypothesis. Check whether your hypothesized value is inside the confidence interval. Okay, but I said there's going to come a time, or there will be a set of tests that we have to do differently. And we're now at that point. So I'm going to introduce you all to a new tool called the chi-squared test, which is for testing what we call the goodness of fit of a model. Okay, but let me take a couple steps back and talk about an example. Imagine that we go out and we conduct a survey and we interview 100 people and we ask them which candidate they intend to vote for. They, and some of them, 56 say that they'll vote for candidate A, the remaining 44 say they'll vote for candidate B. And the question on my mind might be, do these 2 candidates have equal support? Right? Is the proportion of people who will vote for candidate A equal to the proportion who will vote for candidate B? Right? As a hypothesis, the proportion voting for A will equal the proportion voting for B. And in fact, like in this case, it's going to have to be 50-50, just as a note. But, that's the question on my mind. Okay, and we know how sampling goes. Even if it's the case that in the population, half of people like each candidate, we don't expect that our sample is going to be exactly 50-50 every single time, right? Is 56 versus 44 within the realm of possibilities for what we'd get if the support is actually 50-50? Okay, now we talked about how to test this hypothesis really about a proportion. Like, are we, and we can do this using the Z distribution, because it's really only one proportion being tested. Okay, it's as simple as asking the question, is the proportion who will vote for A equal to half? Okay, and again, I told you all we can construct a confidence interval and test the hypothesis. Okay, but sometimes we have more general questions that aren't quite as simple as this. Okay, and then we might want to ask, how well does our data fit the model? Okay, but, okay, we'll go more generally into the question of how well, does some model fit the data? Okay, so in this example, kind of what we have in mind, or what I have in mind, is a model where people support the candidates equally. It's basically random, which 50-50 chance whether they support candidate A or B. Okay, and you can think that what we can come up with what we'd expect under the model, right? So the expected, if in fact the hypothesis were true, we'd expect to get 50 and 50, correct? Right? I'm just stating what my model is, what my expectation is. And then you can think of this as like what I'm asking now is, how well does this fit the data, okay? And we use this awkward term, goodness of fit. But, you know, goodness, how well? Fit. Well, I mean, think of how clothes fit, right? You might say that my clothes are a little bit too baggy in the legs and too tight in the belly, right? It's a little bit loose somewhere, it's a little bit tight somewhere. Doesn't fit the model perfectly, or the clothes don't fit the model perfectly. Well, you can kind of say the same thing here with this example, right? We expect to have 50, what we actually have are a few more. Sort of like it's a little bit baggy there. You know, it's maybe with group B, we expect 50 people, we get only 44, it's like the clothes fit a little bit too tight there. Okay, but is this really outside of like what we would expect through chance? And we've got a general technique for answering that. As long as two things are true. If we are working with categorical data, okay, categorical variable, and we have the counts in each category. Okay, those are the two requirements for what is called the chi-squared goodness of fit test. Okay. And, all right, this is a testing technique where we have to calculate a test statistic, okay, then look up the critical value, and then ask the question, is the test statistic less than the critical value? Okay, if yes, it means we do not reject. Okay, if no, then we reject. Okay. So here's kind of the general way that we test something using a test statistic, and we have a particular test statistic for the chi-squared test. So I'm going to write the Greek letter chi. It looks like a curly X. Chi-squared. Okay, so chi-squared test statistic we get by adding up over all categories K, the observed number in K minus the expected number in K squared over the expected number in group K. Okay? So whatever model we have, gives us an expectation how many we would expect to find in the category. And so we're dealing with the difference between the observed and expected values. All right, so I told you that example that I just put up was something that we could have done using the z-distribution. Okay, here's something like a little bit fancier where there are 4 candidates and the z-distribution is not going to work now. Okay, so imagine we survey 200 people and we ask them about their preferences for 4 candidates. And the counts we get are 56, 44, 39, 61. Are people equally split among the 4 candidates? So think of that as the hypothesis that I'm testing. Okay, the hypothesis is that there's equal support, or if we want to write this in terms of proportions, the proportion who like candidate A equals the proportion who likes candidate B equals the proportion who like candidate C equal the proportion who like candidate D, okay, is a complete statement of the hypothesis against the alternative that at least one proportion is different. Okay. So, again, we have an alternative hypothesis, and the opposite of all those things being equal is that at least one of them differs from the others. Okay. So, think of this now in terms of expected, okay? What would be the expected number in each of these categories if the null hypothesis is true? Okay, so remember, the expected means that we assume the null hypothesis is true. And then, like, what are the numbers that we'd expect to find in the categories? Okay, so we have 200 people. If it's the case that the 4 candidates are equally liked, then we expect to have 50 people in each group, correct? Okay, so it's just 50, 50, 50, and 50. Okay, now, let me write up the difference between expected and observed, right? So 56 minus 50, we have 6 more people in that group than we expected. Okay, for group B, we observe 44, we expect 50, so we have 6 fewer than expected. Group C, we have 11 fewer than expected. In group D, we have 11 more than expected. Okay. So, got it? Okay. Now, in a sense, what we're doing is testing whether these differences are substantial enough to care about them. And one thing that I'll say is that the direction of the difference doesn't matter to us, in a sense, like being 6 above, 6 below, those are off by the same amount. And a way that we get rid of the positives and negatives could be squaring the values, right? And that's really the logic behind the test. If you square them, they all become positive. And so you're talking about the squared difference. Okay, so the last column that I'll put here is the squared difference. Okay. 36, 36, 121, and 121. Okay. So, final thing that I should have done here, when I stated my hypothesis that I wanted to test, I needed to name a confidence level. So 95% confidence. Alpha equals 0.05. Okay. Now, according to the formula, our test statistic is calculated by, it's all right, this is a chi-squared value. Our test statistic is calculated by adding over all categories, the observed number in the category minus the expected number squared divided by the expected number in the category. Okay, so we go through these 4 categories, right? A, B, C, and D. And first category, observed minus expected squared. Oh, I calculated that just a second ago. That was this 36 right here, right? So 36 over, and it needs to be over the expected number in the category, 50. Plus, then we move down. Next category, the square difference is 36. The expected number in the category is 50. Okay. Third category, the square difference between what we observe and expect was 121. Again, divided by the expected number in the category, divided by 50. And then for the final category, group D, also 121 over 50. So, the answer is 314 over 50. Okay, so that's what, 6.28 is our test statistic. Okay, now we have to go and look for some values in a new table. Okay, we can't use the Z table, that was for the Z distribution. The T table was for the T distribution, so the chi-squared table is going to be for the chi-squared distribution. And your textbook also has a copy of the chi-squared distribution. With the chi-squared distribution, we have to pay attention again to degrees of freedom. Okay, and the degrees of freedom are the number of categories minus 1. Okay, so in this case, number of degrees of freedom is 4 minus 1, 3 degrees of freedom. All right, now I'm going to pull up this chi-squared table. Chi-squared table looks like looks like this. All right, let me move it down a little bit. Well, move it on the screen. Okay, here's our chi-square table. And, okay, nice thing about the chi-square distribution, we no longer have to worry about one-sided versus two-sided tests. Everything is going to be out in technically one tail, because things get squared, like the tail of the distribution is only the right tail, the positive tail. There is no tail going infinitely far out to the left. All the values have to be positive. So we really only have to worry about two-tailed, we don't have to worry about the distinction between one-tailed and two-tailed tests. Okay, so we're looking up for the degrees of freedom are 3. So we read down this column on the left for degrees of freedom. 1, 2, 3. Okay. And then we have our alpha. 95% confidence means alpha equals 0.05. Okay, so we read down the column for 0.05. And here we have our answer, 7.815. Okay, so to describe this properly, chi-squared of 0.05 is 7.8. Okay, so now we've got the two important things for testing the hypothesis. We have a test statistic with a value of 6.28. We have a critical value of 7.8. When we test the hypothesis, we ask the question, is the test statistic less than the critical value? In other words, is 6.28 less than 7.8? Okay. Well, in this case, that's what it amounts to. And the answer is yeah, correct? Yes. So we do not reject the null hypothesis. Okay? In other words, or like to say that again, like when we look at these data and we have the 4 groups, the numbers in the groups are 56, 44, 39, 61, that's not enough to deviation from being equally spread that we can reject the hypothesis that all the candidates have equal support. Okay, any questions? Questions? We're good? Let's talk through another example. Okay, now we have 5 candidates. And, okay, the numbers are different. But again, let's test the hypothesis that these candidates have equal support. Okay? So what that means is we can add a new column here for the expected number in the category if the null hypothesis were true. Okay, so with 200 people, 5 candidates, how many would we expect support each candidate? easy math. 40, yeah, okay. 40, 40, 40, 40, and 40. Okay. When we test the hypothesis, we also need a confidence level. Okay. Let's do 99%, just to change things around. In other words, alpha is equal to 0.01. Okay. Now, two things we need to do. We need to find our critical value, and we need to calculate our test statistic. Okay. So let's do the test statistic. Okay. Test statistic is we calculate for each group the difference between the observed number in that group and the expected number in the group squared. We divide that by the expected number in the group. Okay? We do that for each of the categories, and then we add them together, sum them together. Okay. So I'm going to actually write that last step in the table. This is expected, or that last expression, expected NK minus observed NK squared over the expected NK, number in the category. Okay, so category A, we observe 61, and we would expect 40 under our hypothesis. Okay, so 61 minus 40 squared divided by the expected number is 40. Okay, second category, we observe 58, we would expect 40, so this will be 58 minus 40 squared over 40. Okay, third category, 41 minus 40 squared over 40. Fourth category, 22 minus 40 squared over 40. And then the final category, we observe 18, we would expect 40, square that, and divide by 40. Okay. A little bit more calculation here. Let's see, so this is 21 squared over 40. Okay, this is 18 squared over 40. This is 1 squared over 40. Okay, now we have negative 18 squared over 40. And then finally, negative 22 squared over 40. Okay. All right, 21 squared. We need to calculate these, so I'll pull out my calculator. Okay, 21 squared is 441 over 40. Okay, 18 squared is 324 over 40. 1 squared is 1 over 40. Negative 18 squared is same as 18 squared, 324 over 40. And then finally, 22 squared is going to be 484 over 40. Okay. If we add these values together, we get our test statistic. Right? Add these 5 values together, and we'll have our test statistic. So let's do 441 plus 324 plus 1 plus 324 plus 484 is 1,574 over 40. So that is now 39.4. So right, chi-squared is 39.4, the value of our test statistic. Okay, we've done the hard work now. We've calculated the value of the test statistic. All right, so next step, we need to find our critical value. So we pull up the table for the chi-squared distribution. Okay, so existing images. Okay. So here we are. Chi-squared distribution. We need to pay attention to degrees of freedom, first of all. Okay, so how many degrees of freedom do we have? Formula says degrees of freedom are equal to number of categories minus 1. Okay? So we had 5 categories minus 1, 4 degrees of freedom. Okay, so we have 4 degrees of freedom, and we want to test this with 99% confidence, so alpha equals 0.01. Okay, so we read down this column, and we have a critical value of 13.28. So we're told the critical value is chi-squared of 0.01 is 13.3. Okay, now, final thing. To actually test the hypothesis, we check whether our test statistic is less than the critical value. Is it? Come on. Test statistic is 39. Critical value is 13. The test statistic is greater than the critical value, which means reject. Okay. Okay. Since the test statistic is greater than the critical value, we reject the null hypothesis. Okay, got it? Okay. So in this case, these numbers are different enough from being evenly spread that we can say some of the candidates have stronger support than others. This is not equal. Now, we can't necessarily say that it's definitely the case that candidate A has stronger support than anyone else, or we also cannot say the thing is candidate E has weaker support than others. We don't necessarily know who is out of line with the others, but we do know that these values are not statistically the same, okay? So someone has high support, someone has low support, they are not equal. Okay, any questions? Now, I'll mention a couple of variations. Okay, first, the proportions or the expected values don't need to be the same. Okay, the expected is not always the same, right? That was simply the hypothesis that I was testing. We could have tested a hypothesis that candidate A's support was twice as high as the others, and we would do everything the same, except we would have, for the expected number in candidate A's category, twice as many as any other category. Okay, so so expected does not need to be the same. However, having said that, often that is the hypothesis we're interested in testing, whether the expected numbers in the categories are equal. So anything is possible. As long as you can express the expected number in each category, the chi-squared test works. Okay. Now, a second thing is, this will be more important. We can also do two-dimensional data. Okay. In other words, like there are two characteristics that people have. Imagine that we want to look at the relationship between candidate preference and gender, right? That's two dimensions to each person in our sample. We know their gender and we know their candidate preference. So think of like a cross tabulation. Okay. Where you have a table that counts up like the numbers in different like cells. I'll show you all an example in a second. Okay. And in particular, for the next example, we're going to do the chi-squared test of independence. Okay, we're going to use the chi-squared test to check whether two variables are statistically independent. Okay. So, here's my hypothetical example. We go out and we survey 100 people, N equals 100 in total. And we ask their preference for a candidate, A, B, or C. We also ask whether the person is male or female. And we count up the number in each category. Okay, so imagine these are the data we get. And we want to test the hypothesis that candidate preference is independent of gender. Okay. Well, remember how we did that with random variables. The idea with a random variable was that if you put up like the probabilities of being in each cell, the probability of, say, being female and preferring candidate A, okay, remember, if independent, the probability of female and prefer A is the probability of being female times the probability of preferring candidate A. Yeah? Okay, that's the idea that we're going to use right now. So to do this, we need to add basically the probabilities into the table. Okay, so let's calculate. Okay, I've got some things here. I'm going to vanish those. Okay, let's add to this table overall. Bless you. Okay. Overall, the number of people who like candidate A is 30, right? The number who like candidate B is 40. Number who like candidate C is 30. Okay. Overall, the number of females is 17 plus 27 plus 16 equals 60 females, and we have 40 males in the sample. Okay. So, if we want to think of this in terms of probabilities, the probability that a randomly selected person is female is 60 out of 100. Okay. Probability that they are male, 40 out of 100. Okay. If you think of these numbers in terms of probabilities, the probability that a randomly selected person likes candidate A is 30 out of 100. The probability that a randomly selected person likes candidate B, 40 out of 100. And the probability a person likes C is 30 out of 100. And now we can calculate how many we expect to be in each group. Okay, so we can do this in two ways. First is maybe think about the probability of being female and liking candidate A, if the hypothesis is true, would be 0.3 times 0.6 equals 0.18. In other words, the expected number is, we have 100 people. So 18, or 0.18 times 100 is 18 people. Right? Probability of being male and liking candidate A is 0.3 times 0.4 is, the probability is 0.12. Okay? In other words, the expected number is 12. Okay, multiply the probability, I'll write that down. The expected number is the probability of that cell times the total number, right? We have a total of 100, so we multiply the probabilities by 100. Okay, then candidate B. Okay, if the null hypothesis is true and gender and candidate preference are independent, we expect the probability that someone is female and likes candidate B to be equal to 0.6 times 0.4 equals 0.24. Okay, in terms of numbers, we expect 24 people would be female and like the candidate. Okay, probability of being male and liking candidate B is 0.4 times 0.4, so the probability is 0.16. The expected number would be 16 people. Okay, moving down to candidate C. Probability a person is female and likes candidate C is 0.6 times 0.3, 0.18. Okay, so we would expect 18 people. And then finally, probability of being male is 0.4, probability of liking candidate C is 0.3, so the probability of both is 0.12, and the expected number is 12. Okay, so at this point, we've got an expected number in each category, right? We've got these 6 different categories, and we know how many we would expect to be in each category if the null hypothesis were true. And so it's a matter of using the chi-square test to compare the observed number to the expected number. All right. So let's test the hypothesis of independence with alpha equals 0.05. Now, I need to address degrees of freedom. Degrees of freedom when testing a hypothesis about independence are the number of rows minus 1 times number of categories. Let me take that back. Number of columns minus 1. Okay, so we have categorical variables in kind of 2 dimensions, right? One dimension is preference, the other dimension is gender. So the rule for calculating the degrees of freedom, number of rows, that's like the number of different candidate preferences. So in this case, we have 3 rows, 3 minus 1, times number of columns. And there are 2 categories for gender here. So 2 minus 1. Okay, so 2 times 1, and we have 2 degrees of freedom. Okay. So, catch my breath. We're going to have to calculate the test statistic next. Okay. For the test statistics, focus on the observed number in each category compared to the expected number in the category. Okay. So, expected numbers in those categories. Okay. The test statistic is calculated by adding up observed so we add up the observed number in the category minus the expected number in the category squared over the expected number in the category. Okay. And we have these 6 categories that we're dealing with. Okay, so let me go through them. Okay, and I'm going to try to do the 6 categories sort of like geometrically aligned with the table. Okay, so first, that top left cell of the table. The observed number is 17. The expected number is 18. So it's 17 minus 18 squared over the expected number is 18. Okay, top right. Okay, the observed number is 13. The expected number was 12. Square that over the expected number, 12. Okay, moving on to the middle row. The observed number was 27. The expected number was 24. Squared over the expected number, 24. Okay, middle row, second column. The observed is 13. The expected is 16 squared over 16. Okay, then moving to the third row. We observe 18. We observe 16. We expected 18 squared over expected 18. And then bottom right, 14 observed minus 12 hypothesized over squared and then over 12. Okay, so it's a lot of arithmetic at this point, right? Basic arithmetic. So let's see. Top left, so that's -1 squared is 1 over 18. Plus, and then we have 1 squared is 1 over 12. It's 1/12. Okay, plus, let's see, 27 minus 24 is 3 squared is 9 over 24 plus, okay, then we have -3 squared, still 9, over 16 plus, and then, let's see, -2 squared is 4 over 18 plus, and then 2 squared is 4 over 12. All right, and now it's a bunch of math that does not simplify much. All right, so it's time for a calculator. 1/18 is 0.0556 plus 1/12 is 0.0833, okay, plus 9/24 is 0.3750. Next is 9/16, so 0.5625, and then 4 over 18 is 0.2222. And 4 out of 12 is 0.3333. Okay, now when I add these together, I get an answer 1.63. Okay. Assuming that I've done all the math correctly, that's the value of our test statistic. Okay, got it? Okay, so good. Only one more step. We need to look at the table for our critical value. So we go to the table for the chi-square distribution. And let's see, number of degrees of freedom. In this problem, we had 2 degrees of freedom, right? And we wanted to test at the 95% confidence level, so alpha equals 0.05. Okay, so our critical value is right here in the table, 5.991. Okay, so I'll write the test statistic for 95% confidence is 5.991. I'm sorry, the critical value is 5.991. So now we check, is the thing that we calculated 1.63, is that less than the critical value? I see one person nodding yes. Okay, so since 1.63 is less than 5.99, what do? Reject or not? Do not reject. Okay, the hypothesis. And I'll state, the hypothesis we were testing was that the variables were independent. Okay, so in this case, these data do not show a difference between the voting preferences of men and women. Got it? Okay, it does not look like a systematic difference. Okay, does that help you all? Okay, like, kind of stare at the table for a second and the numbers that we originally had. If you look at those, it appears that like men are sort of evenly split among the three candidates, right? Roughly equal among the three candidates. But women, we see more support for candidate B than the other candidates. Is that a real difference, or is this just sort of luck of the draw? Okay, our answer is this is consistent with just luck of the draw. It does not look like a deviation from independence. We can't reject independence and getting these results. Okay, so again, like, does that make sense? This is why, like, using data and doing hypothesis testing is very helpful to know whether something is sort of a fluke in a sense, that like that large number who appear to support, that large number of women who appear to support candidate B, like, is that just something random that happened, or is that a real difference? Okay, and there's not enough, if we compare the men and the women, that's not enough of a deviation to reject that the voter preference is independent of gender. Okay, so.
After doing this
Yeah.
a few times, or I don't know how many times you've done this, but I'm sure you've done it a lot. Like, can you eyeball it?
Can you eyeball it?
Like, can you eyeball it?
Right, but can I eyeball it? Sometimes yes, sometimes no. It's always safest to double check. When I come up with examples, I don't put a whole lot of